So last time we had an introduction to higher order differential equations, and we did some examples with second order. We should do a little bit with something higher, so we'll do a third order example. All right, so here we go. Given that x, x squared, and e to the x are solutions of this differential equation, show these solutions are linearly independent. Okay, we'll remind ourselves what that means. Also, find the particular solution satisfying some initial conditions. All right, we'll work through that. Now, good news is, what do we have? Well, we have a third order differential equation. That's what that third derivative tells us. But notice it's a linear third order differential equation, and it's also homogeneous. These are things we like. Now you might say, well, wait, x squared, that's not linear. No. It's how the y's are related, right? It's, you see the y prime, y double prime, y triple prime. The x's, they can do whatever they want, but it's the y's that determines whether or not we're linear. All right, so we have to do two things. Check linear independence, find the particular solution. Notice we don't have to derive that these are solutions, and we don't even have to verify. Why? Because the problem doesn't ask us to. And pro tip, do what the problem asks, don't do what the problem doesn't ask, because you're spending time. And oftentimes time can be better used somewhere else, like on an exam, right? We want to get all the points. So here we go. How do we test linear independence? Well, one word, Wronskian. So the Wronskian is our linear independence testing machine. All right, so what are we going to do? Well, we have to remind ourselves. We're going to compute the Wronskian of our three functions, x, x squared, e to the x. All right, so the first step. Now, the Wronskian is a determinant, so let's set up our determinant. In the first row, you write the functions, x, x squared, e to the x. In the second row, you write those derivatives of those functions, 1, 2x, e to the x. In the next row, you write the derivatives of the derivatives, right? So every row, you keep taking another derivative, 0, 2, e to the x. And we stop. Now, how do we know we should stop here? We want something square. Since there are 3 columns, 3 functions, we'll want 3 rows. All right, now, our next thing is we need to take this determinant. Now, the way you take a determinant, well, there's actually a couple of different ways. So we're not going to say, you must do this or you must do that. We're going to say, well, use what you're comfortable with. Now, what I like to do for 3 by 3 is I like to work with diagonals. And so I'm going to think of, there's down diagonals. I'm going to be adding those. And there's up diagonals, and I'll be subtracting those. And let's just go through and we'll demonstrate what we mean. So for the down diagonals, well, you have the first one, x times 2x times e to the x. And so that would give us 2x squared e to the x. Then we'll have x squared e to the x, and we hit a wall, wrap around. So then that's x squared e to the x, 0. Well, that's 0. And then we have e to the x, 1, 2. Multiply those together, and we'll get 2 e to the x, all right? So we did our diagonals going down. Now, we're going to do our diagonals in the other direction. So now, we're going to go up. So, for example, 0 times 2x times e to the x, well, that's 0. And because we went up, we're going to not add 0, we're going to subtract 0, because, of course, that'll make a big difference. Well, not for 0, but for other things it might. Then 2 e to the x wrap around x. All right, so that's 2x e to the x. We'll subtract that. And finally, we'll have e to the x and 1 and x squared. Say, okay, great. So that's going to be x squared e to the x, and subtract it. Okay, so now we just clean it up. Of course, we can get rid of the zeros. We can combine our x squareds, and when we do all of that, what ends up happening? Well, we get the following. This is going to be our x squared e to the x minus 2x e to the x plus 2 e to the x. So I'm just going to go ahead and factor the e to the x out. So here is our Wronskian. Now, can this be 0? And we're going to keep things real. So can this be 0? Well, e to the x, well, that can never be 0. So, okay, good. What about x squared minus 2x plus 2? Well, you can find the roots. You'll see it's complex. You can also do a little bit of completing the square. So you can think of this as x squared minus 2x plus 1 e to the x. So, if you have x squared minus 2x, divide the minus 2 by 2, that's minus 1. Square it, so you need to add 1. And this is the same as x minus 1 squared plus 1 e to the x. And now I say, look, I square it, that's always going to be a positive, greater than or equal to 0. Add 1, great. So this is always at least 1, and e to the x is positive. So this is always positive. And so, since it's not 0, then we know they're linearly independent. All right, good. So this is our verification for linearly independent. All right, so that's that step. Done. Okay, now I said there are other ways that you could have taken this determinant. So let's grab another piece of paper here and talk about an alternative way to take this determinant. You may have heard of something called cofactor expansion. Now, keep in mind, you can take the determinant however you like, but I want to show you both ways. And you should do the one that you're comfortable with. And so, if you're comfortable with what you just saw, great. If you're like, no, that's not how I learned it, then maybe here's how you learned it, and you can do that. And that's great. Just make sure you have a way to take the determinant. So how does cofactor expansion work? Well, the moral is you pick a row or a column. Now, in practice, you look for lots of zeros, but let's just be naive and say, well, we'll always go with the first row. Okay, so we say, hey, we're going along the first row. So there's our first row. Now, here's what happens. You go along the first row entry by entry, and you say, okay, first off, there's an x. You say, okay, great. So write down the x. So we're in the first entry. Now, imagine that you cover the first row and you cover the first column. Okay? Now, why the first column? Because that was where the x came from. And what do you see? Well, you see a smaller matrix. So you write that down. 2x, e to the x, 2, and e to the x. And notice it's still a determinant. All right. Now, we go to the next entry, which is x squared. So we say, okay, x squared. And again, cover up the first row, cover up now the second column, and you see that you have, again, a matrix. So you write that down. 1, e to the x, 0, e to the x. Finally, we go to the last row, which is, we see the entry there. Sorry, not the last row, the last entry on that row, e to the x. Okay, cover up that row and that column and write down the entries. So 1, 2x, 0, 2. All right? So again, you write down the entry and then you cross out the row and column it's in and write down the smaller matrix. One more detail, and this is an important detail. and it's one that often gets overlooked, is you have to keep track of the signs. So you're going to add, subtract, add. And in general, if you have a 3 by 3 matrix, there's a sign pattern. It looks like a checkerboard. And so just remember plus, minus, plus. So plus, minus, plus. Now, what have we done? Well, instead of having a 3 by 3 determinant, now you have a bunch of 2 by 2 determinants, and you just go through one at a time. And what do we see? We see x, and here we'll have 2x e to the x, because 2 by 2s are easy. Subtract 2e to the x, and then minus x squared, and then we'll have 1 times e to the x, subtract 0 e to the x, and plus e to the x. 1 times 2 is 2, 0 times 2x is 0. And if we go through carefully, we have 2x squared minus x squared, which is an x squared e to the x. We also have a minus 2x e to the x, and a plus 2e to the x, and lo and behold, we have the exact same determinant. All right, so that's the other way to do it, cofactor expansion. So whichever way works for you, great. That's wonderful. Just make sure you have at least one way that works. Now, that's the first half. There's a second half, which is we need to find the particular solution. Now, when we're looking for particular solutions, and we're taking advantage of the fact we have linear and homogeneous, that means we get to do superposition. So, all right, superposition. This is just a nice way of saying, oh, we can combine our solutions that we know to make more solutions. In fact, because we know these are linearly independent, we know for sure now that all solutions to this differential equation have the following form, namely some constant times the first solution plus some other constant times the second solution plus a third constant times the third solution. So every solution looks like this. So now it's just a matter of saying, well, what are the right values for A, B, C? And once we find that, we're done. Well, what do we need? Well, we need to know something about the derivative and the second derivative. So we'll go ahead and take those. So y prime, well, that's A plus 2bx plus c e to the x. And y double prime, what's that? Well, 0 and 2x, whoops, no, not 2x, 2b. Haha, I almost wrote down not 2b. Whoa, that would have been terrible. And then c e to the x. On a side note, you may notice something here. x, 1, 0, x squared 2x2, e to the x, e to the x, e to the x. Coincidence? No, not a coincidence. So in some sense, you don't even have to think about taking the derivatives. You already did it when you did the Wronskian. Or you can just say, hey, I already did it when I did the Wronskian. Let me just use what I did before, which is great. Recycling. Good for math, good for the environment. All right, now, plug in. We know that y of 0, well, what do you have? 0, 0, c. And that has to equal 5. Y prime is 0. What do we have? Well, we have A, 0, and C. And what does that need to equal? Well, positive 2. Y double prime is 0 is nothing there, 2b plus c. And that has to equal negative 3. Now what we have here is 3 equations, 3 unknowns. And admittedly though, this is, as 3 equations, 3 unknowns go, pretty straightforward. It will not always be this straightforward. And so just be ready, be ready. Don't be surprised if things can get a little messy. But it's the same philosophy. What do? Well, when in doubt, simplify. Can you knock out a variable? Combine things together and in such a way that instead of 3 equations, 3 unknowns, 2 equations, 2 unknowns. And just sort of chip away a little bit at a time. Don't think like, you have to do it all at once. No, a little bit at a time, a little bit at a time. You'll be fine. Now in our case, we're in pretty good shape because we say, oh, well look, C has to be 5. Then we're told that A plus C has to be 2. But we know that C is 5. So A plus 5 equals 2. So we say, oh, well that tells us that A has to be negative 3. Now here we have 2B plus C, which is 5. So 2B plus 5 is negative 3. So that says what? Well, that one we might want to write stuff down. So subtract 5, 2B would be minus 8. So that says B is minus 4. All right, there we go. So putting this all together, what do we have? Our final answer, we take our values that we found, put it in for y. So we have that y is equal to minus 3x minus 4x squared plus 5 e to the x. And we're done. That's the idea. So with our basic tools, we can test for linear independence, we can use superposition, we can solve for our constants. And on a side note, when you use superposition here, you always end up with a system of linear equations. And so that's why we stress so much the importance of learning linear algebra, because it does show up quite frequently as we go on in math. All right, good. Our example from last time, our practice is done. Now on to something a little new. At the end last time, we talked about solving a constant coefficient second order differential equation. Now, that's when, of course, we have a very special form, ay double prime, by prime, cy equals 0. Well, there's another kind of differential equation which is very similar. This is called an Euler equation. And Euler, his name is all over the place. He was quite a productive mathematician. And of course, I'll tell you, when I was growing up, I didn't know how to pronounce his name, and I knew about Euclid, so I always thought this was Euler, but it's Euler. Like, you want to oil something, you're an oiler. And so what is this? Well, it's ax squared y double prime plus bxy prime plus cy equals 0. In other words, you're going to add powers of x matching with your derivatives. Can we solve such a thing? And well, the answer is yes, because if we introduce something, we're going to be able to at least make some progress. And so, okay, what's the idea? Well, the idea is, let's take this new thing and relate it to an old thing. This is often how math and science works. It says, can I take this and reduce it back to something I've done before? So what can we do? Well, we said we can do constant coefficient. So can we turn this into a constant coefficient? And the answer is yes. So the way we're going to do it is we're going to let x be e to the nu. Well, if you want, you can call it a v. And so it's our new variable. Or if you like, v, nu is log x. And now we say, okay, great. Well, what does this do? Well, now we're going to go through and say what happens to our various pieces. So of course, y is a function of x. That's y of e to the nu. Now, what's the derivative of y with respect to nu? Well, we can take the chain rule here. Derivative of the outside, that's dy dx. Times the derivative of the inside. Well, the derivative of e to the nu is e to the nu. That's a great thing about exponential functions. But wait, we know that e to the nu is x. So we get x, y prime x, because that's what dy dx stands for, y prime x. What about the second derivative of y with respect to nu? Well, how do you take a second derivative? You take the derivative of the first derivative. And so that's what you're seeing here, is we're just saying, look, take the first derivative and take the derivative of that. Now, all right, so what will happen? Well, take the derivative of the derivative, And similar to what you have here, well, it's a chain rule. So it's the derivative of the outside, that's where you get the second derivative, times the derivative of the inside, because this is really a function of x. And remember that x is e to the nu, so that's where that e to the nu is coming from. This is a chain rule. And so the derivative of dy dx times the second function, and then the first function, dy dx, times the derivative of the second function. And then we say, well, what do we have? X makes x squared, y double prime of x. Then we have x, y prime of x. Now, here's the great thing. Starting with this differential equation that we have, we say, well, let's rewrite it. So namely, we'll have a x squared y double prime plus xy prime plus b minus a xy prime plus cy. Now, the claim is that this part matches with that part. All right, well, what can you do? Well, what you can do is you can say, hey, just check it, right? Multiply a x squared y double prime, check. A xy prime, and there's a minus a xy prime, cancel. Then there's a b xy prime, check, and there's a cy. Now, why rewrite it? Well, because we want to connect to what we were doing here. So this first piece, we say, look, as if it was meant to be, because it was. This becomes the y, second derivative of y with respect to nu. This part, well, that becomes the first derivative of y with respect to nu. And then, of course, y is y. And what do you see? Aha, this is constant coefficients. And why do we like that? Well, because we have, we have a method. So that's why we like that. So now we can use our tools for solving constant coefficients and solve this differential equation in terms of nu, then go back to x. Now at this point you're probably thinking like, do you have to do it this way? And maybe, but honestly there are alternatives. So here's another alternative. So let's talk alternatives. The other alternative is to say, wait a second, I have a vague recollection of doing something like this way back at the start of our discussions of differential equation, which was to say, let's just put in our guess of y equals x to the r. And when you do this, then what you'll end up doing when you take the first derivative, the power of r comes down, so rx to the r minus 1, and the second derivative will be r times r minus 1, x to the r minus 2. So when you plug in, it reduces to the following. You're going to, because of the powers here, all the powers will be the same. You pull the powers out, divide through, and you end up with a times r minus 1 plus b times r plus c equals 0. Now, one more thing to note. What do you see here? Well, if you expand, you get a r squared plus, here's a minus ar, a plus br, that's b minus ar plus c equals 0. Do these coefficients look familiar? They're these coefficients. What? That's so much simpler. Right. And you end up at the same point. And now you solve for r. And off you go. Now, the only thing that this is a little bit more subtle on is how do you handle repeated roots versus how do you handle distinct roots? So if your roots are distinct, so what happens? Well, for distinct roots, what you'll get is you'll get some constant x to the first root plus some constant x to the second root. Okay, no surprise. What if they're repeated? Now this is where things get a little bit subtle, and we talked about this with constant coefficients before. So if they're repeated, okay, so they're the same root, ax to the r. Now, what would you do? Well, you'd want to have bx to the r. But the thing is, these aren't distinct functions, so you have to have a correction term. Just like we had to have a correction term when we were doing constant coefficients. What's the correction term here? Now, back then, it was you add a factor of x. That's not what we're going to do here, because these are powers of x, so that's the wrong thing. So what's the clue? Well, now we say, oh, here we're thinking of solving the differential equation in terms of this new variable, and so if we had it repeated, we'd add a factor of nu. So what does nu do? It's log of x. So that is what goes here. So if you have repeated roots, you add in a factor of log of x. So that's the alternative. And for a lot of people, this is a little bit easier to remember. Just remember how to handle the repeated roots. So let's see an example of this. Solve 9x squared y double prime plus 3xy prime plus y equals 0. This is an Euler equation. It's a differential equation, it's linear, and we see that the power of x matches the derivative it's attached to. Okay, so what can we do? Well, let's talk about the process we just did where we had this sort of substitution. Namely, we introduced this new variable, and we said, all right, nu is log of x. And what happens? Well, let's suppose we remember the formula. Well, we shouldn't have a hard time. We just wrote it down, right? We say, look, we're going to turn a, b, c and in the Euler equation, and we're going to end up with this equation down here. So I'm just going to go ahead and say, great. So what ends up happening is that this is now going to become the following, namely 9 d squared y d nu squared plus, now here, this is going to be our, so this is, write this down, so a, b, c, so this next term should be b minus a. So this will be 3 minus 9 dy d nu, and then we have y. Or, if you like, 9 d squared y d nu squared minus 6 dy d nu plus y equals 0. All right, now from here, we have constant coefficients. So, at this point, let's turn it into our nice differential, our nice algebra equation, right? So 9r squared minus 6r plus 1 equals 0. All right, the coefficients become the coefficients, and then the powers of r correspond with the derivatives of y. Now, does this factor? The answer is yes, and it actually factors pretty nicely. It's 3r minus 1 times 3r minus 1. And if you weren't sure, what would you do? Well, you could play around with it for a while, or you could just say, look, let me just try quadratic formula. We can convince ourselves that this is right. 9r squared, good. Minus 3r is minus 6r, and then plus 1 equals 0. All right, well, now at this point, we know our values for r, so they're 1/3 and 1/3, repeated roots. So, what does this tell us? Well, in terms of nu, that tells us that our differential equation looks like the following, namely some constant e to the 1/3 nu plus some other constant times e to the 1/3 nu, but because it's repeated, you have to add in a factor of nu. Now, is this our answer? Well, no, because we added this new variable. So we should get back in terms of what we started with. All right, so we need to rewrite it in terms of where we began. So to help us do that, well, we say, look, we know that mu is log x. So this becomes a e to the 1/3. Well, let me put it down a little bit here. Natural log of x plus b natural log of x e to the 1/3 natural log of x. Now, this is correct, but we can do a little bit more. For example, notice we can bring the 1/3 inside. And if we do that, what do we get? Well, we get a e natural log x to the 1/3 plus b natural log of x e natural log x to the 1/3, which becomes a x to the 1/3 plus b natural log of x and x to the 1/3. And so there is our solution. Every solution to this differential equation has this form. And we saw a moment ago, I said, look, if you have repeated roots, you're going to end up with a natural log of x. It's because when you have repeated roots for constant coefficients, you have this factor here. And how does mu relate back to x? It's the natural log of x function. And there we go. Great. If you had solved it by saying, look, guess y equals x to the r, find the roots, just remember, don't forget that natural log x. Life is good. Life is wonderful. So now we want to talk about our general strategy for solving these linear ordinary differential equations. We've talked a little bit about homogeneous and using our superposition, but now what if we have our full generality, we have this nth order differential equation, and maybe we have something on the right hand side. What do we do? What do we do? Well, there's a process here, and we're going to work through the process. So the first step says, well, take this right-hand side, and it's some function, replace it by 0. Now, it might be 0 to begin with, in which case things are simpler. But if it's not 0, replace it by 0, and find our solutions to the homogeneous differential equation. We should find n of them, and they should exist. Now, sometimes we can find it ourselves, especially if it's something where we have constant coefficients. Sometimes they'll be handed to us. And but we say, okay, great, let's find those. Then we know that by superposition, all of the solutions look like some constant times that first function we find, all the way up to some constant times that nth function we find. And we call this our YC, complementary solution. And so it's very complementary, like, you're looking marvelous today. My goodness, is that a new hat you bought? You look great. All right, so that's our complementary solution. All right, now on to the next step. Well, we say, okay, well, we replaced f of x by 0. What if it's not 0? Then we just need to find one solution. One solution to rule them all. One solution to bind them. Now, what is this? Well, this we're going to call our particular solution, y sub p. It satisfies exactly what we need it to satisfy. In other words, when we plug it in to the left-hand side, out pops our f of x. Now, you might notice we put an order here. It's really important to do step 1 before you do step 2. And the reason is that the way that we often go about getting our particular solution builds off of our complementary solution. So we're going to talk about this later, not that much later, so in the near future. We're going to talk about various ideas. One idea is called variation of parameters, which is a fun idea. But of course, the other idea is called undetermined coefficients, or as I might call it, the method of making a really good guess. And we'll explain what that means, as I said, when we get to that. All right, so now we have two pieces, our complementary and our particular solution. And here's the great thing. All solutions, every solution looks like the result of adding them together. So you add the particular plus the complementary. And so now we know what all solutions look like. And the last thing is, well, what if you have some initial conditions given? If you do, well, we know what all solutions look like, and we just need to find the right values for C. And so we use the function from the previous step to solve for the initial condition. Now, here's sort of how I like to think about it. And I like to think of what's going on is if we look at our left-hand side. So our left-hand side, here we go. I'm just going to box it just for reference. I want to think of this as a machine. And so we have the following picture. We have I must say all my machines look the same. So here's our left-hand side. In other words, we throw in a function, and what happens, out pops our nth derivative, all the way down to our a0x, y. Now, we know that for this machine, we actually have two things. We have the following. We know that when we plug in our y sub p, well, what happens? When you plug in y sub p, out pops f of x, because it solves the original solution. All right, so my picture is going to get a little bit crowded here, and so bear with me as I keep drawing these little machines. So these are all left-hand side. If you plug in your particular solution, out pops f of x, because that's what step 2 does. It says find a solution which satisfies this relationship. So it says, okay, you found something such that when you found a function for y, that when you plug it into this machinery, you get f of x. We also know what's happening. Well, that when you plug in the y sub c, what comes out? Well, the answer is 0. Because the way we found y sub c is we made that 0, and we said, okay, what, when we plug it in, gives us 0? And so here's the great aha, because we're dealing with a linear differential equation, when we add these together, we say, well, look, y sub p plus y sub c, when we throw it in to our left-hand side, the result is going to be the same as if we throw them in individually. So we can just throw in our first part. So we throw in y sub p, and we can throw in our second part, y sub c. And what do you get? Well, here you get f of x, here you get 0, and so the final result is f of x. In other words, it is a solution. Now, what are the two pieces doing? The particular solution, that's helping you make sure that you get f of x. Great. What is the y sub c doing? The y sub c is saying, let's get a full range of functions. And so the y sub c says, I can help you get any set of initial conditions you want. That's what yc does. So yp says, I make it work. Yc says, and I'll help you get the initial conditions. And their powers combined, you can solve for everything. And so that's the basic idea. So there we go. So now we have a strategy. Other than, of course, how do you actually find these pieces and how do you find that piece? But, besides those details, we have a plan in place. So let's see an example where we can carry that plan out. So for the differential equation, y double prime minus 2y prime minus 3y equals 9x, verify that y equals 2 minus 3x is a solution. Also find the solution where y of 0 equals 6 and y prime of 0 is 5. Now, notice it's very particular with its words. A solution versus the solution. And it says, okay, so we have to sort of distinguish. Because there's many solutions. Whenever you have a differential equation, you're going to have a whole family of solutions. And so this is just one of them. It's saying, well, find one that has a nice property. Okay, well, we have to verify. All right, so let's just do that. So we start the process. So, let me go with a darker color here. And so we start the process. Y is 2 minus 3x. Y prime is going to be the dirt of that, which is negative 3. And y double prime is dirt of that, which is 0. Okay, so y double prime minus 2y prime minus 3y is 0. Subtract 2 times negative 3. Subtract 3 times 2 minus 3x. Well, okay, this becomes 0, a plus 6, a minus 6, and a plus 9x, which is 9x. So, good. We've now verified that this is a solution. Now, in terms of the framework we just went through, what would we call this? We would call this the particular solution. See, the particular solution is just one solution which satisfies the differential equation as written. So in this case, they said, we will hand you the particular solution. They've given it to us on a platter. How generous. Thank you for doing that for us. Okay, so we know y sub p is 2 minus 3x. Okay, so that's not the final answer, but it's going to contribute. So we'll just mark that. Now, what's the other thing we need to do? Well, we need to find the complementary solution. So, all right, let's work on that part. So, what do we have? We have y double prime minus 2y prime minus 3y equals 0. So when you're doing the complementary solution, you set the right-hand side to 0. And now we say, this is nice. This is something we can do. Constant coefficient, linear, homogeneous are great. Yes! Because we can solve this by turning it into algebra. So we turn this into a quadratic, r squared minus 2r minus 3 equals 0. And finally, it's like, a quadratic we can factor without stressing too much. So we want two things to multiply together to give negative 3 and add to give minus 2. Well, can you think of numbers that do that? Well, it has to be 3 and 1 because that's only 3 factors. One has to be a minus, one has to be a plus. And because we want a minus 2, probably something like that. Well, check. Doesn't hurt. R squared. Good. R minus 3r minus 2r. Great. And then minus 3. So our roots are 3 and minus 1. Now, we take that, we say, okay, well that tells us something about what's going on. Namely, we say, our complementary solution looks like a e to the 3x plus b e to the minus x, right? The roots become what's up in our exponent. They're distinct roots, and so that makes life easy. Okay, so there's the other half. All right, and now we channel and say, we have these two pieces. And we say, all right, great, combine. Their powers combined, they will give us all solutions. And so, now we know that all solutions, every possible solution to this differential equation has to be of the following form. We'll start, doesn't matter which one goes first, so I'll put the particular solution 2 minus 3x plus a e to the 3x plus b e to the minus x. All right, now, are we done? Well, not quite. We have found all the solutions. We started with one solution, now we found all of them, but we have to find the one. What is the one? Well, okay, so now it's time to find a and b. And when you're solving for a and b, this part will come into play because it's involved. So it's not like you solve for a and b independently of the particular solution. No, the particular solution will sort of fudge a little bit with your conditions. So let's see how that looks. So we have y. Let's look at y prime. So that would be negative 3, derivative here, plus 3a e to the 3x, and minus b e to the minus x. So what is y of 0? Well, it's 2 from the here, plus a plus b, because e to the 0 is really easy to compute. And that equals 6. And y prime is 0. Well, that's minus 3, 3a, and minus b. And that's going to equal 5. And so, when we clean this up, this is the same as a plus b equals 6 subtract 2, 4, and 3a minus b is 5 added to 3, because we're going to add 3, which is 8. So in particular, notice it's not 6 and 5 on this right-hand side, it's 4 and 8. That's because the particular solution contributes to when you're solving for your coefficients. And so it's important you keep it there. It's important you keep track, because if you don't, you end up with the wrong values. All right, we're very close. 2 equations, 2 unknowns, bread and butter. This is stuff that we can do in our sleep, we hope, right? Well, add, what happens? Well, you get 4a, b minus b is 0, equals 12. So what does that tell us? Well, that tells us, oh, a is 3. Now, notice, plug it back in, we have 3 plus b equals 4. What does that tell us? It tells us b is 1. And so now we can plug those numbers and we get our final answer. The 2 minus 3x, our particular solution, plus 3e to the 3x plus e to the minus x, which is our complementary solution where we've worked out the right coefficients so that everything is just right. Just right. And there we go. Life is good. Life is wonderful. We've had some good practice. And come back next time and we'll do more. Learn more stuff. Isn't it wonderful? All right. Bye.